Hi, my name is Matthew O'Toole, and I'll be talking about reconstructing transient images. And I'd like to start off by showing you an example of such an image. So this scene contains a fiber optic cable that will glow when you attach a light source to one end. And so we've taken a picosecond laser, attached it to one end of the fiber, and used this picosecond laser to send very short pulses of light through the fiber. Now, a transient image records how that light interacts with the scene at picosecond timescales. Specifically, this image sequence shows how that very short pulse of light is actually propagating through the fiber. And these types of images are actually very useful for all sorts of applications. For example, you can use it to try to understand how light scatters through materials, or try to use this to capture 3D geometry. And later this session, we'll hear a little bit about how we can use these types of images to see around corners. Now, our paper focuses on how to capture and process transient images. And there are generally three different types of technologies for doing this. The first is to make use of optical interference, which is a technique that actually tends to be very sensitive to vibrations that occur within an environment. Another approach is to make use of devices known as street cameras, which tend to be extremely bulky and expensive. And yet another approach is to use conventional time-flight sensors, which are based off of PMD sensors, photonic mixer devices. Now, these are sensors that are really designed only to capture depth maps from a scene. So when you apply them towards transient imaging, they tend to produce relatively poor results, meaning that these transient images have poor temporal resolution. So instead, our paper focuses on a device known as a single-photon avalanche diode, or SPAD, to capture our measurements. And here's how a SPAD works. So we start off with a picosecond laser that sends a very short pulse of light into an environment. That light will interact with the scene in complex ways, and then eventually that light will hit our sensor. When a photon strikes a pixel on the sensor, the SPAD creates a time-stamped event. This is basically a time value that represents the time it took for that photon to travel from the laser, through the scene, and then onto the sensor. Now, we only get one timestamp per pulse, so we repeat this process 50 million times a second. And we collect basically histograms that represent the distribution of arrival times for those photons, one histogram per pixel. And what we read out from the SPAD is a spatial temporal image that basically collects all of these histograms up together. Now, given that in our case, our SPAD consists of a linear array of pixels, we must scan the scene one line at a time to capture a transient image. So the scanning process takes about a minute for 320 different scan lines. And once we've stacked all these raw spatial temporal images together into a volume, we can then play back this volume as a video by slicing the volume up along the time dimension. Now, the raw output of the SPAD tends to be actually pretty noisy, and there's some uncertainty in the time stamping mechanism, which causes the output to appear blurry along the time axis. So one of the technical contributions of our work involves our proposed framework for jointly denoising and deblurring these transient images. We take as input this unprocessed transient image, which has wavefronts of light that appear blurrier than usual, and then apply our framework towards getting a processed version that makes the wavefront much sharper and cleaner. If you'd like to hear a little bit more about our system, the processing framework, or SPADs in general, I suggest that you come visit our poster. Thank you.